Namaste and welcome to yet another lecture on mathematical foundations for machine learning. We were looking at the joint distributions of random variables, and in specific we were looking at the joint moments of the random variables, and we were discussing the correlation and then the idea of covariance, and we made a very interesting statement towards the end of the last lecture. What was that? It says if the random variables are independent, then they are uncorrelated. However, if they are uncorrelated, they need not be independent. Yeah, that is exactly what we concluded the last class with. He said independence implies 0 covariance. However, 0 covariance does not imply independence. We will say need not imply independence. We will come to a very specific case, by the time we conclude this lecture, we will come to a very specific case and see what happens there, right. Okay, good. So, the question is covariance is how they are joint, how the two random variables are jointly varying, like what is the joint spread of the two random variables, because we saw variance to be the spread of the random variable. So, this is going to be the joint spread of x comma y. So, what are we looking at? We say that look, the joint spread of the random variable is basically the covariance of x comma y, and we said the covariance of x comma y equal to 0 implies, okay, let us just look at this, let us go back to the mathematics and probably we will try to understand it a bit better. So, let us look at that. Recall the definition of covariance. Covariance of x comma y is equal to expected value of x y minus expected value of x into expected value of y. This is what we had. Now, covariance is equal to 0. If covariance is equal to 0, then we have 0 is equal to E of x y minus E of x into E of y, which implies E of x y is equal to E of x into E of y. Remember, it is a very easy way to get misguided here. The moment you say covariance is 0, you say E of, you see that expected value of x y is equal to expected value of x into expected value of y, because you put that is equal to 0, naturally the right hand side is basically the difference of two of them. That means the difference being equal to 0 says that the two quantities are the same. That is precisely what we have here. So, it gets very tempting for us to even say that look, we have seen if the random variables are independent, we have said that expected value of g of x into h of y is equal to expected value of g of x into expected value of h of y. We had that. So, it is very easy to get carried away by this and then say look, expected value of x y is equal to expected value of x into expected value of y. So, does that mean they are independent? So, many people what they do is the moment they see this covariance is 0, blindly they say that look, the expected value of the product is equal to the product of the expected values, therefore x and y are independent. No, you remember we did this in the previous class. We said that if the variables are, if the random variables are independent, then the product of the expected values, the expected value of the product is equal to the product of the expected values. Vice versa is not true, right. The vice versa term, that means the converse is not true. If expected value of x y is equal to E of x into E of y, they need not be independent. But it is quite tempting to see that look, yeah, this is 0, E of x is equal to E of x y is equal to E of x into E of y. Therefore, what people do is you extrapolate this, you take it further down, you say that okay, integral or summation x I y j, double summation x I into y j into p x of y, p x y of x comma y is equal to sigma x I into p x of x into sigma y j into p y of y j, and say that look, the joint probability mass function is equal to the product of the marginals and therefore they are independent. No, that is wrong, you can't do that. We will take a specific example right now and see how this could actually be a misguiding thought, what do you call a thought which is not correct, right. That temptation that we have to immediately conclude that they are independent. How does it not work? Let us look at that. Let us consider a simple example. See, to prove we need extensive steps. To disprove, if you have a counter example, one counter example, that is sufficient. If you have a counter example, you can disprove things. So, we are going to take an example and see like what happens. Okay, suppose I consider this example. I am going to give you joint probability mass function of let us say 4 points on the xy plane. So, I am going to take 4 points, let us say this is the x axis and that is the y axis. I am going to take 4 points here, namely let us say 0 comma 1, 0 comma minus 1, 1 comma 0, minus 1 comma 0. Okay. Now, what I am going to do is I am going to say that all these 4 points are equiprobable. That means, we have a joint PMF that assigns equal probability of 1 by 4 to each of the points. To each of the 4 points in the above figure. Okay. Marked above. Okay. So, now what I am going to do is I will just do this business. First of all, let me figure out let me draw the table, joint probability mass function table, then we will be able to understand it better. So, we have x and y values, right, we have so I am going to have this as the joint PMF table. I am going to write y here, y is equal to minus 1, y is equal to 0, y is equal to 1, those are the 3 values that y can take, and I am going to have x is equal to minus 1, x equal to 0, x equal to 1 to be the 3 values that you have seen in the figure. X can take minus 1 0 1, y can take minus 1 0 1. Now, what does it say? It says look, the joint probability mass function assigns equal probability to the points, what the 4 points, that means minus 1 comma 0 has a probability 1 by 4, then we have 1 comma 0 to have a probability 1 by 4, 0 comma minus 1 has a probability 1 by 4, minus 0 comma 1 has a probability 1 by 4. If you see here, these 4 points are here, 0 comma 1, 0 comma minus 1, minus 1 comma 0, 1 comma 0. So, that is precisely what we have marked here, minus 1 comma 0, x is equal to minus 1 comma 0, this is the one, x is equal to 1 comma 0, this one, y is equal to x is equal to 0, y is equal to minus 1 is this, x equals 0, y is equal to 1 is this, right. All the other probability mass functions probability values are all 0, right, this is known. Now, what I want to do is I want to calculate the marginal probability mass functions, which I can do by summing up individual columns, that will give me the probability mass of y is equal to minus 1, probability mass of y equal to 0 and probability mass of y is equal to 1. Similarly, I can sum along the rows, I will get PMF of x equal to PMF of x, basically the probability mass at x equal to minus 1, probability mass at x equal to 0 and probability mass at x equal to 1. So, let us look at that. So, this probability I will write this as Px of x, I am doing it along the rows, I am write Py of y which will be along the column. So, this is going to be along the rows. So, what I am going to get? I am going to get 1 by 4, 1 by 4 plus 1 by 4 which is half, then there is 1 by 4 probability. Similarly, I have 1 by 4 here, 1 by 2 here, 1 by 4 here. So, that is the probability mass function. So, let me write the individual probability mass function here. So, I will write Px of x and x takes the value minus 1, 0, 1, x equal to x is equal to this, and p x of x is, when p x of x is 1 by 4, 1 by 2 and 1 by 4. So, this is the table that I have for the marginal probability mass functions. This is marginal PMF of x. Marginal PMF of x, marginal probability mass function, and I can write it for y also. Let me do that. Y equal to y, the values that y can take are minus 1, 0, 1, the probability values are 1 by 4, 1 by 2 and 1 by 4. From the marginal PMFs I can compute the value of expected values of x and expected value of y. So, let me write E of x. E of x in this case is minus 1 x into p of x, summation x into p of x. So, let me write this, this is nothing but a sigma x into p x of x. So, which is nothing but minus 1 into 1 by 4 plus 0 into 1 by 2 plus 1 into 1 by 4. So, 0 into 1 by 2 is 0, then you have minus 1/4 plus a 1/4 which is going to be 0. The same holds good for E of y. E of y is also the same business that we are going to do. E of y is also sigma y into p y of y, which is nothing but minus 1 into 1 by 4 plus 0 into half plus 1 into 1 by 4. So, 0 into half will get knocked off, then you have a minus 1/4 plus a 1/4 which is again 0. Therefore, what we have here, we have E of x is equal to E of y is equal to 0. Now, I want to find out what is expected value of x y, because the covariance is nothing but, recall that the covariance of x comma y is nothing but expected value of x y minus expected value of x into expected value of y. This is what we have. Now, I want to compute my expected value of x y. So, E of x y, let me see what is that. E of x y is nothing but double summation over x over y. What do I have? X I into y j into p x comma y of x I comma y j, right. This is what we have here. So, let us write this. So, what are we going to have? This is going to be minus 1 to 1, this is going to be minus 1 to 1 x I into y j into p x comma y of x I comma y j. So, what is that? First of all, I will write this as keeping x I is equal to minus 1, I will say minus 1 into y j can be a minus 1, in which case the probability function, the probability mass is going to be p x y of minus 1 comma minus 1. We see from the table that p x y of minus 1 comma minus 1 is 0. So, I am going to get this as 0 plus minus 1 into 0 into 1 by 4 plus minus 1 into plus 1 into 0, right. Plus, let me take x I value to be 0, whatever I take with 0 it is going to be multiplied with 0. So, I am going to have this as 0 into 0 into 0 plus 0 into 0, 0 into 1 into 1 by 4. Then the third term I am going to have multiply, take x is equal to 1. So, I am going to have 1 into minus 1, and the probability of x comma y being 1 comma minus 1 is 0, plus I have 1 into 0, and the probability of x comma y is equal to 1 comma 0 is 1 by 4, and I have 1 into 1, the probability of x and y taking the value 1 together is basically 0. Now, if you see here, every term has one number which is 0, every term is basically multiplied with 0. In the first row you see the probability, either the probability is 0 or one of the digits, one of the numbers is 0. In the second case, if you see all the numbers are 0, you multiply it by 0. In the third case again it is like the first one where either the probability is 0 or the coordinate is 0, therefore, E of x y is equal to 0, which means now what I have my covariance of x y, which is nothing but expected value of x y minus expected value of x into expected value of y is equal to 0. That is interesting, which means covariance of x y is 0. So, what is the question that we started off with? Our question was, does covariance equal to 0 imply independence? So, what is your answer? Of course, we wanted to say that look, covariance equal to 0 does not imply or need not imply independence. So, your answer naturally should be yeah, they are not independent, but how do we say that they are not independent? First thing, you do not really have to do computations here, because if you try to do, I mean you can prove it through computations also, saying that okay, p of x into p of y is not equal to p of x comma y. For example, you take this minus 1 comma minus 1, p x y of minus 1 comma minus 1 is basically 0, which is not equal to p x of minus 1 into p y of minus 1 by 4 into 1 by 4. You can say it that way, right. The joint PMF is not equal to the product of marginal PMF, but you can also do one more thing. Why compute? Let us see if by inspection we get they are independent or not. Now look at this figure that we started off with. What does it say? It says look, whenever there are only 4 points that we have taken here, and each of those 4 points have a probability 1 by 4. Now what it says is, whenever x takes a value minus 1 or plus 1, y always takes the value 0, and whenever y takes the value plus or minus 1, x always takes the value 0. That means the moment you know the value of y to be 1, you know that x cannot be anything else other than 0. The moment that you know that y is equal to minus 1, x cannot take any value other than 0. That means knowing that knowing the value of y, you know what is the value of x. And what does that mean? That simply means it is not independent, right. When it gives complete information about what is the other value, that is exactly what we were looking at, even in terms of events we were saying that look, we were talking about mutually exclusive events and independent events. Independent event means the moment I tell you y takes a value minus 1, I should be clueless about what is the value that x takes, whereas in this case what we see here, the moment I tell you y takes a value minus 1, I can very clearly say that x takes value 0 and it cannot take anything else other than 0, which means knowing y, I get complete information about x. Similarly, when I say x is equal to minus 1, there is no other value of y that can happen, y has to be 0, that is what is given here, y is 0. Similarly, when I say x is equal to 1, there is no other value of y which can occur for this particular value of x, and it has to be 0. That means knowing x completely tells me what is the value, gives complete information about the value that y can take. Therefore, we see that the covariance of x comma y equal to 0, we are going to say does not imply independence, imply independence. Now something strange happens here. See, the covariance is also, it involves the correlation. Correlation is going to be say some kind of similarity or something. You say that look, the covariance is 0 means we end up saying that look, they need not be independent. That means there is some relation that exists which is not captured by this covariance of x comma y, and that is precisely why we say that they need not be independent. If there is a relation, I mean if there is no relation, then we say that they are independent, and you could say that look, okay, then naturally the covariance is 0, but in this case the covariance is 0, that means there is some kind of a relation that exists, but that relation is not something which is being captured by the covariance. That is why we say that it does not imply independence. Is the understanding clear? Like correlation is similarity, a similarity measure. Covariance contains this correlation term. Covariance is 0, meaning okay, we do not know there could be no relationship. We could actually be tempted to say that there could be no relationship. If it is no relationship, then naturally they must be independent, but here it says look, they are not independent. That means the relation between x and y is something else which this covariance is not able to capture. So what we are going to say is this covariance that we have here, it captures linear relationship between random variables. Anything non-linear, this covariance will not pick up, and therefore it will say it is independent. That is what we are going to see in a completely I mean we will do it in a minute from now. Okay. So what we are going to say is we are going to say that look, we will do a small task here and then get to understanding this whatever statement that I made a couple of minutes back. There is some kind of a non-linear relationship that exists. So we will look at it in a bit now from now. Okay. Okay. So this does not imply independence. So there are two questions that arise here. Is there a specific case where covariance equal to 0 imply independence? So is there a case where, okay, we will come to this independence case through in a different from a different perspective right now. Okay, let's pay more attention to this covariance of x y. Covariance of x y is nothing but expected value of x y minus E of x into E of y, right. Now E of x is nothing but the average value of x or the expected value of x, and E of y is the average value of y. We will take a very specific case where let us say x is going to be weight measured in kgs, in kilogram, and y is the height measured centimeter. Therefore, the covariance of x comma y is a quantity which whose unit is measured now in very specifically in the above case. In kg centimeter, that means it has some units of measurement. Now assume that okay, we have measured weight of let us say 10 people in India, where the weight is measured in kg and the height is measured in say centimeters. Now I take these 10 people to another country where a different unit of measurement is taken. For example, you take them to the US where the weight is measured in pounds and height is measured in inches. It is the same set of 10 people whose height that I have measured here in centimeter and weight I have measured in kg in India. Same set of people, I take them to US and then I measure the height and weight. The height is measured in inches and weight is measured in pounds. Now the covariance there is going to be having a unit which is nothing but pounds inches. right. Pounds inches is going to be the unit. Now what does that mean? Now you can actually convert kgs to pounds and then centimeters to inches, inches to centimeters and pounds to kgs. You have this conversion factor that comes into picture, right. Let us take another interesting example, forget about this kg centimeters right now. Let us take another simple example where let us say x is basically the cost of let us say laptops that you buy in India, which is going to be in rupees, and y is going to be the cost of mobile phones that you buy in India, where the cost is again going to be rupees. Therefore, the covariance of x comma y, that means the covariance of your mobile phone cost and the laptop cost, if you see, it is going to be measured in rupees squared. Now I want to buy the same set of mobile phones, I want to look at the cost of the same set of mobile phones and the same set of laptops in the US, I am going to measure it in dollars. Now if you say that okay, there is a conversion factor where $1 is now going to be let us say 80 rupees. Now what happens when you do in when you get whatever that you get in terms of rupees here, when you buy it in terms of dollars, I am going to get to that conversion factor which I am going to multiply it with 80 times rupees that I am going to do. So it is 80 into 80, 6400 you are going to get, and that way whatever that you buy in India, that gets multiplied by let us say 6400 there abroad, right. Therefore, the serious problem here, which means whatever that the laptop cost versus the mobile phones cost that I do here, which is I am going to measure, for which the covariance is going to be measured in terms of rupees squared, in the US it is going to get multiplied by let us say 6400 times some number. That is, so can we say that look, in India the covariance is smaller and when you go to US the covariance is larger? It does not make sense. Since covariance is dependent on the units of measurement, there is a serious problem like what we saw now. In rupees it is some number, in dollars it is going to get multiplied with say 6400 into that number, which says that it has got high covariance there. It does not make sense because you are going to buy the same commodity except that the units of measurement is going to change. Now this is a quantity which is dependent on the units of measurement. We want to get rid of this unit of measurement because units of measurement says that in one place it is the same quantity you are measuring, in one place it has lower correlation or lower coefficient covariance, at another place you have the same things which have higher covariance or higher correlation. How does that even make sense? It does not, right. So how do we do this? That is exactly where you remember we had done this in case of single random variable, we did moments about the origin, moments about the mean, that means the central moments. What we are going to do is we are now going to capture the standard moment, standardized moment. So what I am going to do is I want to get rid of this units of measurement because that is giving me a headache. The units of measurement is now going to dictate the covariance. What was smaller in one place is going to be a large number in the other place, that is going to be a bit scary. So how do we get rid of this? How do I make it dimensionless? I need to basically divide it by a quantity, this covariance, I need to divide it by a quantity which is basically having the same units as your E of x and the same unit as E of y. If I do this, then the numerator by denominator, the units, I mean you basically get into a ratio which is a dimensionless quantity. So the question is, what is the number with which we need to divide, what is that quantity by which we need to divide this whatever we have done. That means we have covariance of xy to be equal to expected value of, you remember this, x minus expected value of x into y minus expected value of y. This is what we had, and of course that expression will boil down to here after simplification. That is, let us not worry about it for the time being. We will say it is expected value of x minus e of x into y minus e of y. Now I want to divide this x minus E of x by some quantity and y minus E of y by some quantity such that covariance of x y, which I am going to give a different name to it, such that I get into a dimensionless quantity here. So, what is it that I divide this E of x, x minus E of x by and y minus E of y by? Now, one thing that you can do is you can straight away divide it by the expected value of x. Expected value of x is nothing but it has the same unit as whatever is there in the numerator. Expected value of y has the same unit as y minus E of y, whatever that we have here. So, you could divide it by it, but that is not correct, because expected value of x and expected value of y are typical numbers. You remember in physics, when we have a vector, I want to get a unit vector. If I want to get a unit vector, what do? I basically divide by the length of the vector. You have studied, all of you would have studied that if you have a vector u, I want to get a unit vector, what you do is you divide this vector u by its length. U by vector length u is going to give me a unit vector in the direction of u, and vector length v by v vector divided by vector length v is going to give me a unit vector along the direction of v. Now, there is a problem. So, what is it that we can do? I have to get to the idea of a length measure which is going to normalize that to a unit vector. So, what is that length measure that I can use here? There is one distance metric that we have here, one length metric which we have here, and what is that? The standard deviation. Standard deviation has a length metric, right. So, it is basically the distance from how far are the values from the mean. So, you are going to have some kind of distance metric. So, what do is I divide these two quantities by the corresponding standard deviation, and I am going to get to a new quantity called the correlation coefficient, rho x comma y. I am going to call this as the correlation coefficient. So, how am I going to define this? This is going to be expected value of x minus E of x divided by sigma x into y minus E of y divided by sigma y, where sigma x sigma y are standard deviations of x and y respectively. Right. I have this. So, let us see what it is. So, I am going to define rho x comma y, which is nothing but expected value of x minus E of x divided by sigma x into y minus E of y divided by sigma y. So, this is nothing but I will pull this out sigma x sigma y, I am again going to get expected value of x minus E of x into y minus E of y, which is nothing but covariance of x y divided by standard deviation of x into standard deviation of y. This is what I am going to call this as my correlation coefficient. So, this is a dimensionless quantity, and what we will do is in the next class when we come back, we will figure out the properties of this correlation coefficient, and we will see that this actually measures the linear relationship between the random variables x and y, and anything non-linear this will not be able to pick up, and that is precisely why we say that if the correlation coefficient is 0, you say that it does not have a linear relationship, or they are uncorrelated in the linear sense. The sense they do not have a linear relationship, it could be any non-linear relationship, but that non-linear relation is basically not captured by rho x y, and that is what we will see in the next class. Thank you.